Welcome to Stage 1 Physics. Our new topic is going to be called momentum. You would have heard this term momentum used in everyday language, yet it is a physics term. So now when we talk about momentum, we might say a small football player needs a lot of momentum if he's going to tackle a big player. We might also say a train has a lot of momentum as it is hard to stop. Now this use of momentum, we have to think about what it means. In physics, momentum is associated with moving bodies. A good picture of momentum is a measure of how difficult it is to stop the motion of a body. So I'll ask you a couple of questions. Is it harder to stop a train rolling at 5 kilometers an hour, a car rolling at 5 kilometers an hour, or a bike rolling at 5 kilometers an hour? So now with common sense, it is harder to stop a train moving at 5 kilometers an hour than it is to stop a bike. So we can say a train has more momentum, although rolling at the same speed, than the bike. So we can deduce that the larger the mass, the larger the momentum. Okay, so what about another question I'll ask you? Would it be harder to stop a cricket ball moving at 5 meters per second, 10 meters per second, or 20 meters per second? So I would say it would be harder to stop a cricket ball moving at a greater velocity than it would for a slower cricket ball. A cricket ball on the boundary hit for a 6 will be harder to stop than someone throwing an underarm delivery to yourself from a meter away. From that we can deduce that velocity plays a critical part in momentum, and the greater the velocity, the greater the momentum. Getting into the maths and physics of it, we can use Newton's second law of motion to find a relationship between the mass and the speed of an object that determines how difficult it will be to stop. The textbook that you have actually has a derivation of this formula. However, I have just placed it on the screen, and if you're interested, you can go through the derivation yourself. Okay, so we've got the formula of P equals M times V. Now, P is what we write as an indication of momentum. So P is momentum. M is mass, and that has the standard units of kilograms, and V is velocity, having the standard units of meters per second. Now we must also remember that velocity is a vector quantity. That means that momentum is also a vector quantity. Now having a look at the formula, the units of momentum are related to the mass and velocity. So we have kilograms and meters per second. So our units of momentum are kilogram meters per second. When we have a moving object, we can actually change the momentum of something too. So we can calculate the momentum on an object when it is moving, and due to some force, the momentum of the object changes, and this force we can call the impulse. The change in momentum is due to this impulse, and it is a measure of how much force is applied for how much time. Impulse has a formula force times the change in time, which is also the change in momentum. So the units of impulse are Newton seconds. Now you may remember earlier I said the units of momentum are kilogram meters per second. However, calculating it this way, you get the units of Newton seconds. So both units are interchangeable. Now you can also think of impulse as force required to stop the object. So the greater the momentum an object has, the greater the impulse required to stop it. Now looking at the formula, we can say that a great force can be required over a short period, or a smaller force over a greater period to achieve the same impulse. So when we have a body in motion, with no external forces, the momentum remains the same. So we come to the law of conservation of momentum. If no external force is applied to a system, there can be no change in momentum of the system. the total momentum of system bodies remains constant. So I've got a little animation here of Newton's cradle. When the external ball has energy granted to it by picking it up and releasing it, it has momentum that continues to the second ball. So this momentum is conserved and actually passes through to the final ball where the momentum is transferred and the final ball continues the path. Now in an ideal world, this motion will continue forever. However, due to the friction and other losses, the cradle motion will eventually stop. To put it another way, the initial momentum a system has is equal to the final momentum of the system if no external forces are on that system. Okay, I've got some examples here of two-body collision. So this is a collision between two objects. Okay, so we start with the object, which is object 2, and it is in a stationary position. Now we have another object, object 1, which is moving at a certain velocity. Object 1 comes into contact with number 2 and a collision occurs. So they come into contact. In an elastic collision, the objects actually separate, yet momentum is still conserved. Now we can compare this to case 2, where we've got an inelastic collision. In this case, object 1 comes into contact with object 2, yet it sticks to it. They move as one object after that point. I've got a table here that summarizes that. So we can see the difference between elastic and inelastic collisions before and after. Now there are equations written here as well that can help you determine what the momentum is before and after collision for each object, or in the inelastic case, the final combined object. Okay, so I've got some key equations here that can help you solve problems that involve momentum, and these can be found on your formula sheet. I've got a glossary here as well of the key terms for definition purposes that I've covered in this lecture. My next video will be on solving problems using equations that we have learned throughout this video.